The separation of C8 aromatics, orthoxylene, metaxylene, paraxylene, and ethylbenzene is an industrially important separation. Due to the closeness of the boiling points, distillation is not a viable technology. However, there are significant differences in the freezing points of molecules that allow fractional crystallization to be used in industrial separations of C8 aromatics. On cooling a liquid mixture of C8 aromatics, the first crystals to form are those of paraxylene that packs most efficiently in the liquid phase to form crystals. My focus is on separation of aromatics using micro-porous crystalline materials, and for background I refer you to my publication in 2019 in Separation and Purification Technology. Let's examine the absorption of xylene isomers in AFI zeolite that consists of 1D channels with a corrugated structure. The distances shown here are 7.3 angstrom from here to here and 8.4 angstrom here. This is the experimental data on the unary isotherms for orthoxylene, indicated by inverted green triangles. The red circles are for paraxylene and the blue triangles are for metaxylene. In order to understand the significantly higher loadings for orthoxylene, we need to resort to molecular simulations of the absorption of these xylene isomers. And if we examine the computational snapshots of orthoxylene, metaxylene, and paraxylene, we note that orthoxylene is a compact structure that allows the orthoxylene molecules to nicely fit into the grooves that have a peak-to-peak distance of 8.4 angstrom. The other two isomers, metaxylene and paraxylene, cannot locate in a face-to-face manner as does orthoxylene, and the absorption of metaxylene and paraxylene is less efficient. That leads to smaller loadings for the unary isotherms. Indeed, configurational bias Monte Carlo simulations of absorption of mixtures of ortho, meta, paraxylene, and ethylbenzene show that the mixture absorption is selective to orthoxylene. This is because of efficient packing of orthoxylene in a face-to-face manner. This face-to-face packing of orthoxylene is akin to that of Pringles. Face-to-face stacking of guest molecules inside micro-porous crystalline adsorbents is an efficient way to achieve entropic separations. The components that pack the most efficiently is entropically favored in mixture adsorption equilibrium. And for any given guest molecules, we can design the shape of the channels in order to achieve face-to-face Pringles type stacking. This concept is described in detail in the paper by Torres Knoop and others in ChemPhysChem 2015. Within the triangular channels of Fe2BDP3, the stacking of 1,3,5-trichlorobenzene occurs in a face-to-face manner. This results in a very short footprint as compared to the footprints of 1,2,3-trichlorobenzene and 1,2,4-trichlorobenzene that cannot stack vertically. Therefore, these Toblerone-shaped channels structures may be employed to selectively adsorb 1,3,5 isomer from a mixture with 1,2,3 and 1,2,4 TCBs. For optimal stacking of para-xylene within an adsorbent, we need channel dimensions which are about 10 angstrom so that para-xylenes can stack vertically. One such candidate is the MOF MAF-X8 that has 10 angstrom channels, and the computational snapshots show that the para-xylene molecules can stack face to face in a vertical manner, and this is also evident in this movie animation.